Okay, welcome everyone. So to this special session of the Quantum Colloquium series, we're very happy today to have colleagues from chemistry and to have Mouzhe Xie from the University of Chicago, chemistry, who's going to tell us about diamond-based quantum sensor for molecular analytics. Please.
Thank you very much. It's really my great pleasure to be here to visit your university at Abu Dhabi. Actually, let's maybe start with phrases. Okay, here we go. Maybe just a introduce myself. My name is Mouzhe Xie. I got my bachelor's degree from Shanghai University in China. Then I went to the Ohio State University. I did my PhD in chemistry, where I use conventional NMR.
There's almost no sound.
Now, in my postdoc research, I actually switched my research field a little bit from conventional NMR to the NV-based NMR that I'm going to discuss more. So in a nutshell, I'm really working on both conventional and optically detected technologies to study biological systems at molecular level. So in general, I'm doing research in quantum sensing. Let me just briefly introduce what is quantum sensing in case you don't know. So typically, quantum sensing describes the use of a quantum system, quantum properties, or quantum phenomena to perform a measurement of a physical quantity. I can give you two concrete examples to show you how powerful quantum sensing technologies are. The first example is a so-called laser interferometer gravitational wave observatory or LIGO. People built on their flat ground a giant, essentially a microson interferometer with these orthogonal arms, each spans about 4 kilometers long. And then when a gravitational wave from the universe comes and hits the ground, it stretches and squeezes these arms just by a tiny bit. So if we can measure such a tiny change in the distance, we are able to detect this gravitational waves and use them as a method to study what's going on in the universe, for example, the detection of a black hole. So for such a parameter, which essentially is a quantum device, and especially with the latest advances in the in using squeeze light, nowadays such a LIGO system can detect a error to the 10 to the minus 23rd, almost 24th power of order that is basically saying within this 4-kilometer arm, it can detect a distance change that is only 10,000 times or 1/10,000 the width of a proton. So it's really a tiny distance that people can detect. The second example concerns about the atomic clock. So we know for certain atoms, the transition frequency is a constant. So the more accurate you can measure such a transition frequency, the better we can do timekeeping. So atomic clock has find their wide applications in many systems, especially in GPS global positioning systems. So with the most advanced atomic clock, I believe published last year or 2 years ago, has already reached a noise level that is 10 to the minus 19th relative error, which means if we use such an atomic clock to measure the entire age of the universe, which is about 13.7 billion years old, the error will be less than 0.1 second. So really, the quantum sensing has allowed some of the most precise measurements that human beings have ever. If you think about it, the quantum mechanics is was formulated exactly about 100 years ago in the 1920s. But in the past a few decades, especially in the past 20 years, there's so many devices that can make quantum science more approachable and more affordable. And it's also worthwhile to point out that last year, the Nobel Prize in Physics was awarded to 3 great scientists who are working on quantum information or quantum informatics sciences related research. I think it's really safe to say that we're really in the era that we can quantum engineer a state of matter and use them to explore new physical quantities that ever achieve, that is ever made possible by the quantum sciences. For me, I am always excited about the biological system. If you think about a cell, if you really zoom in a corner of the cell, you might see something like this. It has basically a very congregated matrix of biomolecules with proteins, with lipids, nucleic acids, metabolites, etc. Each of these biological molecules have their own defined structure. And these biomolecules also interact with each other. For example, here is a pathway map showing the p53 mediated apoptosis process. These molecules are also moving, meaning there's a lot of dynamics in time. And these dynamics within the biomolecules can range from the very fast dynamics in the femtoseconds all the way up to minutes or hours in real time. So I think if we want to really understand at the higher hierarchy how biology works, it is very important for us to go back to the molecular level and structure, their interactions, and dynamics. Therefore, my big vision overall is, can we use quantum device or quantum sensing, which gives us the most precise measurements that human beings have ever achieved to study biological systems. Or to be more specific, I wanted to develop a nanoscaled NMR that is enabled by diamond-based quantum sensing. By the way, NMR is nuclear magnetic resonance. Then in the next 2 slides, I want to try to explain or justify why we want to study NMR and why we want to do nanoscale. So I believe everyone sitting here have ever heard of NMR, and you have used the NMR platform. This is how it looks.
Excuse me?
With basically a chemical cryogenic liquids, and then a superconducting coil that huge magnetic field under which the nuclear state will under splitting and manipulate energy and capture the spectral signature of those molecules. So it's a ensemble measurement. It has high spectral resolution. It does not really require fancy labels like the fluorescent label, and it's also non-invasive, and so many advantages of conventional NMR spectroscopy. Therefore, it has wide applications in physics, biology, medicine, geology, sciences, etc. During my PhD, for example, I have used the solution NMR to look at a few different systems, including the structural determination of proteins and also protein dynamics, in which case we actually mixed protein samples with a little bit of nanoparticles. And because of the presence of nanoparticles, slows down the overall effective tumbling rate of the proteins. And thus it opens the or extend the observation window of internal dynamics from a nanoscale, which was basically set by the tumbling correlation time, or tau c. Now we extend that observation window from nanosecond time scale to microsecond time scale. And also in the context of polymer physics, concerning a special protein known as intrinsically disordered proteins, which are basically polymer chain or peptide that does not really find structure. And we discovered some of the cooperativity in the finding of IPPs on nanoparticle surfaces. And last but not least, also metabolomics. And the goal there is to identify and quantify small molecules by NMR from a biological sample, for example, human serum or human urine. And by doing so, we can monitor those metabolic fingerprints and use it to do early disease diagnosis or monitor people's health. So because of time, I don't think I have get a chance to explain or go to the more details of this, but I'm more than happy to discuss all the technical details during the Q&A or after this session. So for those of you who are interested in a little bit of instrumentation of NMR, you probably know that for conventional NMR spectroscopy, we use a metal coil to do the detection. We put our samples in solution inside of this NMR tube, which is surrounded by a saddle-shaped metal coil. And we use such a coil to do the detection, to basically deliver microfrequency pulses and also use it to detect the precision of this nucleus. However, because of the use of such a metal coil, the sensitivity is actually limited. Therefore, we need a 10 to the 16th spin in order to generate sizable magnetic moment that can be taken out. Now, can we do nanoscale NMR detection? The answer is yes. And we can take advantage of this so-called nitrogen vacancy center in single diamond crystal and use it to do nanoscale NMR. And we will go into discuss more details about the NV center just in a few slides. And this technology has been around for about 17 years. And it was simultaneously developed at a few different institutes and universities. So let's say if now we have such a nanoscale NMR, what could be the potential applications? Well, we can integrate it with the lab-on-the-chip analytics and to detect molecules on chip, or we can use nanodiamonds and put them directly inside the cell, and then we can look at local environment at different parts of the cell. We can also develop them into portable devices or study even single cell physiology, etc. There's a lot of potential of this technology. Just move it up here. So for in the next 30 minutes or so, I would like to divide my talk into the following three parts. Firstly, let's discuss what's the NV-NMR sensor map. And then I'll introduce a recent work that we functionalize the diamond surface in order to put the target molecule on the surface. And then I will briefly introduce an ongoing work that we use a diamond membrane as a sensor in contrast to the conventional bulk diamond. And that is followed by the conclusion and the outlook. So let's start with the sensor mechanism. So this is typically how a NV-based NMR looks like. So to start with, we need a piece of diamond crystal. So it's a single crystal diamond. Typically, it's 2 millimeter by 2 millimeter by 0.5 millimeter in size. And of course, we need to make sure there are NV sensors, the fabricate the NVs inside the. And then for optical readout, we need to build a microscope. In this particular case, it's a confocal microscope. Therefore, we need a pulsar laser to generate green laser, provide the green laser source. And then we shine the green laser on this diamond crystal, and then we collect the emission. So here is a confocal scan of such a sample. Each bright spot is basically a NV center. So the NV system is essentially a spin 1 electronic spin, which means it is a triplet. It has a triplet state. So in the ground state, you can see that it has a ns equals to 0 substate, and there are two degenerated ±1 substates. There exists a optical pathway that if you shine a green laser, you can actually initialize or polarize such a system so that all electronic spins or all electrons goes to ns equals to 0. Therefore, by using a green laser pulse, we can optically pump such a quantum system to the ms equals to 0 ground level. And because of the same pathway, we can actually also read out the quantum state of such a system. The reason is, if it's started with ns equals to 0 state, the emission is actually brighter. It's about 50% brighter than the states in the ±1 state. Therefore, basically, we can actually go to the next slide. In reality, we also study such a system under a magnetic field. And because of the presence of an external magnetic field, the degenerated ±1 state will further Zener split. So now it actually makes it simpler. We no longer have to deal with a 3-state system or a triplet state system. We can select 2 of the energy levels and use them as a spin qubit. In this particular case, it's a ms equal to 0, and then the transition with ms equals to -1. And we can use a microwave to basically drive this transition. And if we keep driving this transition, we can see something like this, which is known as a Ramsey. You can see the oscillation between these two transition energy, between these two transition states. And very importantly, all of this can happen only at room temperature. Of course, if you go to cryogenic temperature, you will see better or cleaner manipulation, but even at room temperature, all of this can happen. Therefore, this is actually a perfect system for biological applications. Now, with such a sensor, how do we do quantum sensing? So the bottom line is any physical quantity that can change energy diagrams can be detected by them. Now, how do we such physical quantities includes a fluctuating electric field, a fluctuating magnetic field, temperature, or strain in crystal. So for us, or for me, I'm very interested in the NMR, right? We use it as a sensor to detect the fluctuating magnetic field. How do we do it? Let's look at this particular case. We have a sensor. It is a sensing volume. Let's say there are some molecules in this sensing volume, and these molecules under a magnetic field will undergo a lower frequency, a lower precision, and will generate a fluctuating magnetic field. That is the signal we're going to detect. Let's say in the frequency domain, that's the signal we're going to detect. Now remember, we can optically prepare our spin state by shining a green laser pulse. And then we can read out the spin state by another green laser and to look at the intensity of the emission light. Now, in between these two pulses, we can add a bunch of dynamical decoupling pulses using microwave. And if we're, for example, this is basically a CPMG type experiment. If we change the spacing between these pi pulses, we can actually change the detection frequency or sweep the detection frequency window. And when that window matches with the inherent frequency generated by the nuclear spin, see a signal. For example, this is a typical benchmarking experiment, which we can detect the proton signal and carbon-13 signal from the objective wall. So we always use it as a kind of benchmarking experiment. You always, in most of the cases, you put the objective oil on top of the diamond to maximize the photon counts, and we can see the NMR signal from the objective oil just by looking at the NMR experiment. Now, what are the different domains or the current techniques of such a NV-based animal? We can discuss two different domains or two different research techniques. The first research example or domain of this is single NV center, meaning there's one single that is there are several. We implement nanometers under the diamond, and it will create a sensitive volume that is so tight that it can only fit in one protein at a time. So the sensitive volume is it is so small that you can fit only one protein at a time. That's actually how we achieve single molecule detection. On the other hand, we can also use a bunch of NV centers, or basically use NV ensemble for the detection. In this case, we no longer need to use a confocal system to drive or to manipulate the NV beam. Instead, we can use a wide field microscope, and we can excite a column or a pillar of NV centers. And because now we're using multiple NV centers all at once, the sensitive volume is much bigger. And finally, so we can increase the sensitivity, but at the compromise, we actually lose the spatial resolution. Therefore, these are the two domains of research we can, or two domains of experimental configurations. And depending on the specific scientific question, we can choose one over the other. So here are a few examples of the current state of the art of this technology. In this first example, the researchers from Harvard University detected the carbon-13 signature from one single ubiquitin molecule that is right on the diamond surface. So this is a kind of a single NV action of single protein molecule, the NMR signature of such a protein molecule. And in this case, or actually the other cases, the researchers used ensemble NV centers to perform NMR. And with that, with the sort of advanced readout techniques, they can distinguish the chemical shift of different molecules. In this particular case, it can actually distinguish these protons versus the protons on the methyl groups. And also, you can look at the decoupling between different nuclei in heteronuclear cozy experiments, and you can even go from a one-dimensional NMR to multi-dimensional. So what is missing currently is that the people really haven't come up with a great way to interface carbon molecules with the diamond sensor. Again, this is a milestone work, phenomenal. However, in this particular case, the researchers just dry the floating solution on top of the diamond surface, and then they put it in objective oil. Yes, they detected a signature, but the floating is sterile. They want to use based quantum sensing techniques to study biological systems. It is very important that we study these systems under their physiological conditions. Therefore, we need a way to biocompatibly functionalize diamond surface so that we can immobilize whatever target molecules we're interested in on the surface and then perform this. That brings us to the second topic of biocompatible diamond surface functionalization method. I can elaborate a little bit more why we want to immobilize target molecules on diamond surface. So NV-based diamond sensing, especially when we're using bulk diamond, is essentially a surface detection method. Let's say we have our NV center. It has NV volume, which is room center supply. And if we have a solution of molecules, these molecules will generally diffuse around. When diffusing, it generates a signal or like bipolar couples with the center, but if it diffuses away, it no longer couples to the NV sensor. Therefore, it will generate a sort of inherent or incoherent signal with the time correlation function or with basically diffusion noise that is generated by the diffusing of these molecules. Now, if we can come up with a way to immobilize target molecules on the surface of the diamond, then very likely we'll get a coherent signal. These molecules are not diffusing away, and also in this way, we can keep tracking the same molecule and study its let's say conformational changes over time. So that is really desirable for quantum sensing. So this idea sounds very simple, but actually it requires a lot of fine considerations because there are so many criteria that we have to satisfy to make it really applicable. For example, we want to make sure that such a functionalization does not have a negative impact of the NV coherence. We want it to be as thin as possible because the thinner or closer our target molecule with the NV sensor, the stronger coupling it will have. Of course, it has to be biocompatible, it has to be stable, and we want this type of conjugation to be specific. And last but not least, we want this method to be recyclable because, of course, diamond is expensive, and not only because of that, once you have characterized a good NV center, you want to use it repeatedly or again and again. And in many cases, you want to do a control experiment to use it before and after a change. Therefore, we really want this method to be recyclable. So all of these taken together make this method. So I did not really explain in detail, but actually the oxygen emanated diamond surface turned out to be having the longest coherence are known compared to Therefore, we just say, okay, let's don't bother about the chemistry of the diamond surface. Just start with a oxygen and diamond surface, and then we can just use atomic layer deposition to lay out a very thin layer of aluminum oxide material on the surface that has a uniform thickness of about 2 nanometers. Now we have already converted the question of functionalizing the diamond surface to functionalizing a oxide. And as chemists, we all know how to do that. It's very easy. We can do a solidization followed by a pegylation. And these methods have been very well established in the single molecule microscopy community for almost 20 years, and people have done very careful study and it will work. So here we just grafted this method on diamond surface. The use of packed molecules has 3 advantages. Firstly, these packed molecules are flexible. We can control the size of the packing units so that the molecules we're going to immobilize, even though they're tethered to the surface, they can still locally move around. So that will give us a little bit of motional averaging for NMR study. Secondly, this packed layer serves as a passivation layer, meaning that biomolecules that are unwanted, they cannot really attach to the surface. They will be, so it serves as a protection layer to avoid unspecific binding. And last but not least, now with a packed layer, we can change the composition of the packed molecules. For example, we can use 5% bulking or bulking-related pack versus 95% being the inert or methyl-terminated tag, so that we can control the density of the target molecules on the surface. We use single molecule fluorescence microscopy to look at it. And here, our model is a single-stranded DNA molecule that has a 5-way diameter. So now we can use fluorescence microscopy to see individual DNA molecules. We demonstrated 2 conjugation methods. The first one is bulking-structure interaction, and the second one is a string-promoted alkyne azide cycloaddition or click chemistry, which was actually the Nobel Prize in chemistry last year. So when we change the functional groups, so the density of this functional groups on the surface, we can clearly see an increase in the density of the immobilized DNA molecules, which are basically these bright spots. And of course, we also tested the stability of this functionalization method. It is stable for a couple of days, which is long enough for NV measurements. So this tells us that the conjugation is specific, and we can really control the density of target molecules on the diamond surface. We did not really say it loud in the paper, but these DNA, stranded DNA, are actually aptamers. They adopt a certain configuration, and through structural recognition, they can further bind their protein partners. In this particular case, it's the aptamer for thrombin. Therefore, we can keep building up the block to further recruit thrombin molecules from the solution to the surface of the blood, stronger in this fluorescence images. Therefore, by doing so, we can actually recruit and enrich pretty much any biomolecules we want to the diamond surface. So it's really a general method. And of course, we care about the impact of this functionalization on the NV coherence. Remember, the longer coherence, the better sensitivity. or in that case, it means less detection time for our system. We really want as long coherence as possible. So on the left side, this is one particular NV center before blue and after in purple on the functionalization. So we did observe a finite decrease in T2 spin coherence, but they're still in the on the same order. And on the right-hand side, we are looking at a few more NV centers, and so just to build up a little bit of statistics, we did observe some decrease, actually a heterogeneous way of decreasing in the NV coherence, but again, they're on the same order. So if we are using such a NV center to detect a NMR signal, for example, it's just some brief calculation. The integration time for these NV centers to detect a single photon spin with signal noise ratio of 1, assuming 5 nanometer functionalization layer, or basically separation of the spin from the NV center, we can detect such a signal within a matter of 16 minutes to a few hours. So this is a kind of from computational perspective, how sensitive our sensors are. Indeed, after basically publishing that work, we continue to now oxide, and now all of a sudden, instead of seeing the decrease of coherence, we actually observed some increase in the spin coherence. And this is we're still working on it, and we're trying to, and we believe what happened is really for alumina, because of the presence of aluminum 27, the presence of aluminum 27 nuclear spin, it actually created a noisy spin band on the surface of the diamond, and that dominates the decoherence mechanism of the NV center. Compared to aluminum 27, TiO2 with much cleaner material that has very little spin noise. And also the reason that we're seeing increase in the TiO2 is basically we're making this NV centers deeper in the diamond, so it's better protected from the surface noise. And also we're seeing better stability using TiO2. So again, this is an ongoing work. We're still trying to collect some data, see really what's going on there. So a quick summary is that by using common labeling techniques, or we use the actin-mediated pull-down experiment, we have developed a biocompatible, versatile, stable, and recyclable functionalization method. And I forget to say something about recyclability, but basically, once we have finished using the surface formulation for this round, we can just soak the entire structure in KOH in the base, and then we'll acid clean, and that will set the surface, and we can keep using the same diamonds crystal for the next round of study. As you can see, we already did before functionalization, after functionalization, and we actually repeated that process quite a few times. So a commentary used the title "Quantum Sensing Goes Bio." I think it's really captured the essence of this work. Now, in the last 5 minutes or so, let me briefly introduce a ongoing work that we use diamond membrane as a new sensing platform compared to the bulk diamond or nano diamonds crystals that many other people will use. So the motivation is the following. When we study biological systems, it is very common that we want to study protein system or nucleic acid, and we want to see how they interact with the binding partner. Therefore, we need to deliver the binding partners or substrate or cofactors very often. We want to change the environment very often. We probably want to change the pH, the salt concentration, and imagine also need to supply and detach the samples of it, and even apply chemogradients. All of this is very difficult to do on a bulk diamond because even though I still have a center doing all the detachment from the backside using the front side open, in reality, most of the time how people do this, they have diamond crystal, they put their sample on the diamond surface, and then they put it upside down in the petri dish, and then have the laser coming through a glass cover slip, look at the surface where the NVs are implemented. So such a configuration will have very little room for us to engineer the full channel system. Therefore, if we can use diamond membrane, just like the idea of a light scan, where all these optics are engineered underneath, leaving the surface or the detection window completely open to sample, now we can press our fingers and get fingerprinted. Here, the same way, we can integrate all the detection optics on one side of the diamond membrane, actually the back side of the diamond membrane, and leaving the sensing side completely open to sample manipulation or in the flow channel. So our collaborators at the University of Chicago, Professor Alex Hai and the senior grad student Xinhan Guo, have developed such a method that using a process of we can kill a very deep diamond membrane, and then just do a plasma and mount or bound diamond membrane pretty much any substrates. So here is one look like. Nowadays, we typically make diamond membrane that is 200 micron in size, with a tunable thickness from a few hundred nanometers, 100 nanometers to 400 nanometers thick, and that thickness is tunable or can be changed in a controllable fashion. Now, if we do a focus on ion beam and look at the crystal structure of the interface under using high resolution TEM transmission electron microscopy, we can really see the diamond crystal, each basically these carbon atoms in a very ordered fashion, and then a amorphous interface, and then into this ordered substrate again. In this particular case, we use a sapphire. So now with this technology, we can bound the diamond membranes on a quartz cover slip, and now we can put it and we can now use wide field microscope. We don't even need the confocal, of course, under confocal scan, you'll see the epicenter, but even at the under a wide field microscope, because the fluorescence background of the diamond membrane is so low, we can already see the epicenters. individual. And of course, we confirm it by looking at the PL mapping. And now with such a device, we can easily flow in and analyze in the flow channel. And we can also use the functionalization method I just introduced to immobilize structivity or structivity conjugated to the quantum dot 5.5 as model system to really demonstrate that we can immobilize the target molecules on diamond surface in the controllable way. And we'll also, this is an ongoing work to keep on identifying all of these details, but basically a preliminary study suggests that the quantum metrology of these MV centers are as good as in the bulk diamonds. Now with such a flow channel, not only can we do molecular studies, but we can also incubate an entire cell inside this flow channel. And again, because of the thin configuration of the diamond memory, we can, instead of only doing active fluorescence, we can perform TIRF microscope. So for those of you who don't know, active means if you find a green, if you illuminate your sample, the laser beam comes straight out from the objective lens. Now, if you filter your laser beam, that can happen at the interface. The total internal reflection will happen, and because of that, only a very thin layer, about 200 to 300 nanometers of the sample will be illuminated. So that's why in these perfect images, you see much cleaner or individual member coatings that are downloadable compared to the API, which is much more blurry. And just to play with the system, we can even put E. coli cells that express green fluorescent proteins. The hope here is that in the future, if let's say we want to study this particular membrane coating, we can just put the NV center in the membrane that is right underneath to do the study. Here the same, if we want to study a live E. coli cell, we can just choose a NV center that is right underneath to perform the study. So that brings us to the conclusion. In the past 30 minutes or so, I have introduced a NV-based nuclear magnetic resonance spectroscopy configuration or platform, and indeed, using the same strategy, we can also perform NV EPR electron paramagnetic resonance spectroscopy. So it is really a emerging molecular sensing technology that has unprecedented spatial resolution, even some single molecules. And also, I introduced a biocompatible surface functionalization method that can help us to immobilize target molecules directly on diamond, which actually saw some more interesting challenges because diamond material is pretty difficult to chemically modify to start with. And also, we are developing this diamond membrane-based sensing platform. Hopefully, by doing all of these methods, we can bring this technology one step closer to real biological sensing. So, in the future, here's what my personal point of view. Many new discoveries and new technology. With conventional method, of course, we're going to transform on our world. But the quantum sensing represents a new direction, new technology that can probably help us to understand the world around us even faster. And I think really the quantum sensing after that is probably going to take over that can help us to get more new knowledge in a very rapid fashion. So here is a little bit of comparison. This is one of the examples, not very representative, but just to show you, in 2004, people can already use a solid state NMR to study ubiquity molecules with a very fine resolution of or chemical shell resolution of ubiquity molecules. But now, with the NMR, we're seeing a very, very broad peak that seems not telling us more. However, don't forget that this is the NMR structure or NMR fingerprint from one single molecule. Therefore, in the future, if the NMR-based NMR can help us to distinguish, for example, domain-domain motions or a different combination of molecules, then very likely we can use it as a method to study some biophysics at single molecule level. So finally, maybe as a advertisement, that I'm starting my own research lab, and I think the research production is really interface of biology. So we're really hoping to use a multidisciplinary efforts to push forward the NV-based biosensing technology. And if you're interested in some of these projects or have ideas or brainstorm, please feel absolutely free to contact me. And with that, I would like to thank all my staff, funding resources, and most importantly, thank you very much for attending the hospitality. I'd like to answer any questions you might have.
Thank you. Questions?
So, etching bulk diamond and functionalizing it is expensive and looks like super complicated. I wouldn't even know how to do it. You showed some pictures of apparatuses that you would need to do that. So I'm wondering, why not just go with bulk diamonds? You can just, nano diamond crystals. You can just throw them into a hydrogel and pattern the hydrogel however which way you like it. So there must be some advantages to the bulk over nano diamonds for this particular application.
Yes, that's a very good question or comment. So nano diamonds are actually also a leading platform that many people use, and the advantage, of course, because there's more and the years of technology, people can easily deliver inside the cell. The temperature inside the cell. It's a very good platform. My only critique about it is that because of the large surface development, the coherence of NV centers inside nano diamonds is much worse than the bulk diamond. Therefore, again, back to the sensitivity issue, if we can have longer than to go with the bulk diamond, with the nano diamonds, like this with the different set.
Slide you showed where the difference in chemical shift achievable by this technique is compared to the actual, let's say, conventional chemical shift distribution that we can obtain already by normal NMR. This kind of difference. So I wonder whether the problem that you were just pointing out of the loss of coherence using the nanodiamonds is not more or less the same problem that you face there, because when you really want to look at a single protein and you just fix this protein on the surface of your diamond and the dot, let's say, you must be certain that, of course, a single molecule is okay, is there. But the very moment you want to increase the sensitivity, and you want to put more than a single molecule, you must be certain that the orientation and the actual motion does not dephase and gives the same kind of loss of coherence that the nano diamond could do. Isn't it the same problem? It is the same problem in the end.
I see your point, and I agree actually to a large extent that by the very end, it's probably dealing with the same challenge. And I guess the question is, nobody really knows what will happen. It's really a kind of new technology for really kind of get down to the very ground and trying to assess all of these details. Of course, you can write down the Hamiltonian.
Yes, you can write down whatever you like. The problem is that we do not know how they are.
How do we compare which one wins, which one loses? I think all of the questions are still to be explored. And I actually agree with you that for single molecule biophysics, the NV platform is, in my opinion, very, very challenging. Not only the orientation you mentioned about, but also probably a more severe challenge is when we focus our laser beam on one in a very localized region, will the protein survive those laser powers, etc. So there's a lot of things that need to be explored, and there's ideas all around. And again, this is a new field. I think there's still a lot of potential to just try to understand these questions. Those are really scientific questions to look at.
I would like also to just stress the fact that this method enables to overcome the problem that, for instance, are met with the nuclear dynamic polarization, because here you can keep the coherence in principle for ages if you're able, in principle. So, I mean, this kind of, it's a real advance, but probably, yes, we have to find the right target to exploit the advantages of this huge, very, very sensitive technique.
I completely agree. Actually, in many cases, it's so sensitive that we actually did some preliminary tests to just moving away from the objective oil to a real biological buffer. We see a lot of unknown things. Basically, these fluctuating or diffusing ions, they are also creating a signal. So there's a lot of things to be sort of decoupled our real signal from the targeted sample versus in environment. So it's almost too sensitive, such a sensitive. So yes, a lot of the work needs to be done. I completely agree with that. And also, since you mentioned about the spectral resolution here, so I wanted just as a clarification, one of the reasons that we see a broad signal versus there, of course, besides all this detection imperfections, is that here we're using a direct magnetic field that can separate. But here we're only using I don't remember. I believe it's a few $100. Therefore, we can in principle build a laser NMR inside a giant magnetic field. Actually, there are ongoing works at the not really on the influencing side, but on the energy side, because now the field splitting is so big, we can no longer use the gigafactories to drive the units. We actually have to almost electronics. So it becomes at some point a lot of engineering challenges. So I'm personally also very excited about those directions. I don't think I will do those in my own lab, but I'll keep an eye on even my own lab. Working as I look forward to see what we can see inside the giant. But in principle, with that, we can better separate the chemical.
Any other questions? Okay, if not, let's thank Mouzhe again for the very nice talk. Thank you. Thank you, everyone.